Welcome everyone to the third chapter of our time series course. Today we will further dive into our dependent processes and we will derive our first simple asymptotic distributions. We will start with a motivating example and review the cornerstones of the IID results that allow us to derive limiting distributions. We then continue with a discussion on several types of dependent processes. In the final part, we will focus on a first example to derive the limiting distribution in an easy model, where we will consider three crucial cases of dependency in the error terms. Note that in this lecture, I'm not following Hamilton that closely. So for me, it's enough if you understand everything that is said in these videos. So let us start with the motivation and a very simple model where we regress yt on xt as over here. The OLS estimator is given by this expression that should be familiar to everyone. Now, our main focus of today are the key ingredients we need to study the asymptotic behavior of our least squares estimator. And if we think back of the roadmap that I laid out last week, our first key step starts from this estimator, then plugs in the DGP as written here in blue inside of the expression of the least squares estimator. You can then expand the product, which gives you this expression. And here you can simplify things a bit because these terms, they simplify to just the identity matrix. Now then you just bring beta to the other side and you introduce the appropriate scaling, which is root t, to arrive at this key expression. Now, it is a good exercise to verify for yourself that you understand all of the steps that are involved in this line to arrive at this expression. Now, what do we have over here? We have two important terms where we need to introduce the appropriate scaling. And from last week, we've seen that this is an average, requires scaling 1 over t, and it calls for the law of large numbers to establish its probability limit. The second term is a scaled average. It requires scaling by 1 over root t, and it calls for the central limit theorem to derive its limiting distribution. Now, while you have seen the law of large numbers and the central limit theorem for IID data, we cannot rely on these versions anymore in our settings, since the independence assumption no longer holds for time series data that are clearly time dependent. So we would like to make use of a law of large numbers and central limit theorem that allows for dependency. Now, these derivations quickly become mathematically very challenging. And so that is why during this lecture, some results will be discussed in more depth than others. Now, the main idea is that after this lecture, you should be able to understand certain key concepts and assumptions that are typically employed, for instance, also when you would be reading articles on this topic. So we will start by reviewing some crucial results of the IID world to see what we can learn from these proofs. And we will first consider the scalar process and then later on move from a scalar to a vector process over here. So let's start by reviewing the weak law of large number for scalar sequences. Let's say that we have t IID random variables whose first moment, so the mean, is mu, and the second moment is finite and denoted by sigma squared. Now let's define the average by x bar over here. And then for a small epsilon, the probability that x bar deviates more than epsilon from mu will go to 0 if t goes to infinity. Or in other words, the average converges in probability to its population analog, namely the mu. Now, which inequality do we need to prove the weak law of large numbers? Well, we need Markov's inequality. And Markov's inequality gives you an upper bound on the probability that a non-negative function of a random variable is larger than some positive constant. And a special version of Markov's inequality arises under the form of Chebyshev's inequality. Namely, when we take x equal to y minus its expected value, and when we set alpha equal to 2 in the formulas above. Then the probability that y deviates more than epsilon from its expected value can be bounded by its second moment divided by epsilon squared. Now, how can we use Chebyshev's inequality to prove our law of large numbers? Well, we start from the probability that x bar deviates more than epsilon from mu. And by Chebyshev's inequality, this can be upper bounded by its variance divided by epsilon squared. Now let us plug in the definition of our average here in blue, such that we can further simplify this variance term. I can already take out the factor t outside, but then I need to square it since I'm taking it out of a variance. And then the variance of a sum is in general not equal to the sum of the variances, but you also need to account for all of the cross terms as well. Of course, in our IID setting, since we have independent copies, all of these cross terms disappear. They're equal to 0. And we are only left with t, capital T, of these variances. Now, they are also all equal since the random variables are identically distributed. So I can just simplify this term by t times the variance of the first, let's say. And then finally, if we let t go to infinity, the desired result follows immediately from this line. Now, let's have a closer look at the key steps in this proof. First, to get a finite variance, we needed to have a finite moment condition. Also, we don't really need the fact that our random variables are identically distributed. As long as actually the supremum over all the second moments is finite, well, that will also do the job. Moreover, also the independence assumption is not really needed. As long as all of these cross terms over here, if they vanish in the limit, then we can also establish our desired result. Now, what are these cross terms? Well, in our case, these cross terms are, of course, special since they contain the autocovariances. So what do we need? Well, we need that these autocovariances disappear in order for the proof to go through. And that means intuitively that there can't be too much dependency in our series. Now, since these autocovariances, they play a crucial role in our time series context, you will inspect them in more detail in one of the assignments. What about the central limit theorem? Well, the law of large numbers states that the average approaches mu, the first moment, as t goes to infinity. The central limit theorem tells you actually much more about the behavior of x bar minus its expected value. It also gives you the speed or the rate of convergence, namely root t. So the central limit theorem tells us that this guy over here converges in distribution to a normal with mean 0 and variance sigma squared. Or in other words, x bar is a root t consistent estimator of mu. And this guy here is big OP1. Or alternatively, the difference is big O1 over root t, since you need to divide by this power of t, or alternatively blow it up by root t in order to get your convergence result. Now, since the central limit theorem tells us more than the weak law of large numbers, we should actually expect stricter assumptions. We obviously need finite variances, so a finite second moment, but we won't dive deeper into the derivations of the central limit theorem. But do make yourself familiar with these big O notations, as we will be using them regularly as of now. And if you're unsure about these, let's have a look at the material that I've put on Canvas.